Okay, good afternoon here in Madrid at the College of Physicians of Spain, and good morning in the Americas. We are very happy to continue with our conference about the future. And we have joining us now from the USA, Dr. John Matter, Senior Astrophysicist at NASA Goddard Space Flight Center, Nobel Prize winner in 2006 in physics, and also he is leading the James Webb Space Telescope. So we are very honored, we are very proud to have you, Dr. John Matter. We are all waiting to learn from you. So please, thank you so much and go ahead.
Thank you. I'm happy to be here talking with you. And I want to tell you the history of the universe as a little bit about that at any rate, and how we learned some of it and what we hope to learn with the upcoming James Webb Space Telescope. So here we see in the picture the great telescope itself as it will be in outer space. You see a great golden hexagon. That is the big mirror that collects the light from the distant stars and galaxies. It is protected by the gray object that you see below it. It is a big umbrella to protect it from the heat of the sun and the earth. And of course, we will tell you much more about it as we go along. This is a joint project of NASA with European and Canadian space agencies. They're all contributing important parts of the observatory. And it is available to all astronomers worldwide, including students. So if any of you are up-and-coming astronomers, you will have another opportunity to propose to use the telescope next year. So it's an enormous project to build this. It's taken since our first conversation in 1995, almost 26 years so far. And we hope to have it working for at least 10 years in space after we launch it. So, however, now I want to step back a little bit and think about the history of the universe. This is what we think we know. The universe is expanding, and it started out very smooth and very, very hot and very compressed. It has been unstable in a huge variety of different ways as it reorganizes the material into more complex systems. It is probably infinite in extent and has no edges, no boundaries. It's very old. It's about 13.8 billion years old. So things that we conceive of as very unlikely, such as our own personal existence, have had a time, obviously, for this to become possible. We have learned in the last few decades that living things particularly use digital codes to store the information about what they should do. So each one of our cells has a DNA code, which is read by decoding devices in each cell. Our bodies have about 30 trillion cells like that. So you can think of ourselves as being one gigantic supercomputer with 30 trillion central processing units all communicating with one another. Obviously extremely complex, and made possible by the fact that the memory is digital. So there's an unlimited ability to store complexity in that DNA. So here we are, survivors of many billions of years of evolution, which I remind people is survival of the fortunate, the lucky people, because this is not necessarily the thing that people used to hope for, which was that somehow evolution was intended or leading definitely to our own existence. We might not be here except for the good luck of some of our ancestors. We've learned as engineers and scientists that we can design systems to stabilize a unstable system. So, for instance, each one of your cells has hundreds and thousands of control devices that maintain the identity despite the fact that atoms are continuously being exchanged with the environment, and most of the atoms in my body have been replaced many, many times. But I'm still here, I'm still myself, and that's a bit of a mystery. So from the physics point of view, we know about the four forces of physics. There are three strong ones, strong and weak nuclear forces and the electromagnetic forces. And those we know are described by quantum mechanics. So quantum mechanics says that everything you heard of that's called a particle actually has a wave nature, and everything that you heard of that's called a wave has a particle nature. So this tells us that we are built out of the combinations of little tiny things into larger ones. So this, in a way, tells us the building blocks of everything. The combinations of atoms into molecules I call the Lego blocks, and they have particular shapes, and we know how sticky they are, how they attach to one another. But it's too complex for us to predict what's going to happen. The fourth force of nature is called gravity, which we now describe by relativity. And this tells us, in a practical sense, how does a gravitating object collapse and turn into something complicated like the solar system. So we know in our school we learn how to calculate thermodynamic things. Chemistry and all kinds of things are based on thermodynamics. We're just beginning to learn as humans how to understand non-equilibrium thermodynamics. So nature seems always to find a way to increase entropy by reorganizing itself into ways that do this. So in particular, complexity can enable natural systems to increase entropy more rapidly than they would have been. So complexity is a natural result of thermodynamics. So how do we know the history of the universe? Well, back in 1929, Edwin Hubble drew us this graph. This is the first one that we ever had that showed directly that distant galaxies are going away from us with enormous speeds, roughly proportional to distance. So this picture was the first one in 1929. So Einstein did not expect this. He was quite sure that it could not be. However, it had been predicted by Georges Lemaitre, a Belgian priest who was also a brilliant mathematician and scholar. And so he knew that this should be true. Now we call this law the Hubble-Lemaitre law. So it shows from the slope of the chart that if you divide the distance by the speed of a particular galaxy, you get an estimate of the age of the universe. This was the first time that we ever knew that there was a thing of an age of the universe. So now we know the actual age is about 13.8 billion years. So how would we know more? Well, in 1948, it was predicted that this great universe of ours should have been extremely hot when it was young, and the heat that existed then should still be here to be measured. So in graduate school, I worked on a project to measure that, and the project failed. Nevertheless, when I got out of graduate school, NASA said they wanted proposals for new satellite missions, and I said, well, let's propose my thesis project for outer space. So we did, and there it is. It actually flew 15 years later, and it worked because real engineers made it work. It took about 1,500 people to do it. Anyway, it did confirm the Big Bang story, as we now call it. I'm not going to show you all the details, but it confirmed that this heat was indeed the remnant of the early universe, and that it has although we consider it a very low temperature, 2.7 degrees above absolute zero, 2.7 Kelvin, it's actually the brightest radiation field in the entire universe by far. So here is the result that we now have. The early universe was very hot and very compressed when it was young. It has no center. Even though from Hubble's graph, you would think you were at the center, we say, well, actually, imagine what it would look like if you were somewhere else. Someone else would also think, living in another galaxy, that he or she was also at the center. So conclusion is there's no center. The universe is expanding into itself, and from the mathematics that we have, there is not a first moment. People often talk about the creation of the universe, but in physics, we have no way to talk about that. We only have ways to describe process, where something changes into something else. So another curious point is that the time of zero, when you imagine running back the clock all the way towards the beginning, is not actually included in the universe we can describe. Because as you run the clock backwards in your mind, the temperatures and densities of the material go up and up and up. And finally you say, I do not know what should be happening. We do not know the laws of nature that should apply. Let's call that the Big Bang. So when people call it the Big Bang, people often think, well, that's like an explosion, a firecracker, like a a small explosion at a particular place in time. This is the exact opposite of the picture that astronomers have, which is that the entire infinite universe is expanding away from itself, into itself. So probably there's no end, although we can't prove that. So how would we know? We were going to take a lot of pictures. Here is the Great Hubble Space Telescope. It was launched a few months after the Cosmic Background Explorer satellite, and it's now 31 years old and is working beautifully because, of course, we repaired it 5 times, and we made it with multiple parts. So if something goes wrong, we have backup equipment. So it's still running beautifully and hope to have it running for many more years. We took a few pictures and confirmed the Big Bang story that I tell you. So then astronomers looked at the results that they got and they said, well, we are proud of this great observatory, but we're disappointed that we cannot answer all of our questions with it. So one of the key questions was, what are the first galaxies like? So they wrote a little book and they said, please just build us another telescope that's even more powerful and that can observe the infrared light that is thought to come from the very first galaxies and that grew out of the expanding universe. So here is another picture of it. It's there's the great golden hexagon. By the way, it's not really solid gold, of course. It is a very, very thin layer of gold because gold is the best reflector for infrared light. We have instruments that come from around the world. There are 2 that come from Europe, 1 that comes from Canada, and the European Space Agency is buying the rocket launcher, which is an Ariane 5, which will carry us into space on December 18th this year. So operations will be in Baltimore, Maryland, as they are for the Hubble Space Telescope. And you will be able to get all of our pictures and information from that spot, just as you already can do with the Hubble. The telescope is enormous. It is 6.5 meters in diameter, and that's bigger than the rocket, which means that we have to fold it up, and I will show you what has to happen after launch to unfold it after launch. So how sensitive is it? If you were a small insect, 1 square centimeter, hovering at the distance of the moon away from the telescope, we would be able to see you, both the reflected sunlight and the heat that you would send out. So it's an extraordinarily powerful telescope, and that means we can confidently expect there's something out there that nobody has ever seen before that we might discover. We have a harder problem looking at really bright objects, but we do have the ability to focus the telescope on all the solar system objects from Mars on outwards. So that's really important to us because all of our solar system objects are the easiest planets to study. All the ones around other stars are really hard. So what are we going to look at? We will take this picture, which was taken by the Hubble Space Telescope, and we will presumably, we hope, do much better. This is the picture that the astronomers looked at and said it wasn't quite good enough for answering all their questions. What we should see, in addition to what's in this picture, are little faint red specks, or actually infrared specks, that represent the very first galaxies to grow in the expanding universe. So we'll be looking at that to try to tell the story of how the galaxies grew from the primordial material into now. We will be looking inside dusty gas clouds. This is a picture called The Pillars of Creation, a place called the Eagle Nebula, where stars are being born today. You see on the left-hand side what the visible camera sees on the Hubble Space Telescope, all these wonderful glowing gases, along with extremely dark and opaque dust clouds. So the stars that are being born now are being born inside those dusty clouds. When you make a telescope that can use longer wavelengths, infrared, you can begin to see inside those clouds and see how the stars are growing now. So that's one of the great wonders and challenges of this telescope. We will be looking at the solar system. There are 2 remarkable places that have fascination for us besides Mars. Everyone suspects that Mars was alive. We also have a guess that perhaps these 2 objects might be alive or were alive before as well. Europa is a satellite of Jupiter and was discovered by Galileo himself. And here is a picture that was taken by the Galileo spacecraft. It shows that Europa is covered with ice, and that there are cracks in the ice layers where you see the brown marks. Once in a while, water comes out between those cracks. So that our next mission to this object is called Europa Clipper. Our plan is to send a spacecraft that will fly through the water jets that are coming out to see if they have organic molecules in them. So when we originally realized that Europa had an ocean under the ice, we thought we were going to have to build a nuclear reactor to melt our way in to find out. Now, we don't have to do that now. We can wait for the water to come out. So that's in our plan. And of course, the Webb telescope will look at this object. The one on the right is a geological map of Titan. Titan is a satellite of Saturn. It's very large, and it's large enough and cold enough that it has a lot of atmosphere, mostly nitrogen. It has lakes and rivers and rain, and those are made out of hydrocarbons. Methane and ethane are the main constituents. So there's a geological story to find out there. There's also the potential that maybe if life can be based on some other system besides the one that we know with liquid water, maybe this will be a place where nature has already done it. So we'll certainly be interested in whether we see any signs of life on this object. Under the surface, by the way, there might be a liquid water ocean as well, but we don't know. We will be looking at planets around other stars. And we have a technique called transit spectroscopy, which is very powerful. If you can watch at the right time, and sometimes a planet will go in front of its star. And so we can say, well, how big is the planet by seeing how much of the starlight it blocks? Now, if you're very good at this, some of the starlight goes through the atmosphere of the planet on its way to the telescope, and you can analyze that for the chemistry. So our aim is to find out if those little planets have any sign of molecules that would say water or carbon dioxide or methane or something else that would say this is not just a rock, this is an interesting planet with atmosphere. So we have small, medium, and large to look at in our catalog. We've already found a great number of these objects. None, on the other hand, are expected to be like Earth. So if you want to know if there's a planet like Earth, we need different equipment. Here's a little capsule history of the Webb telescope and how we get it to launch. Up in the upper left corner, I show you a picture of the telescope as it was in the very clean room at Goddard Space Flight Center, just outside Washington, D.C., where I work. After we put it together there and made sure that it was functioning properly, we took it around to a gigantic shaking table where we were able to apply 50,000 pounds of force to see that it would survive the vibrations of launch, which are terrifying. But of course, have to do this. Then we put it in a shipping container, send it around to the airplane. It's a gigantic military airplane called the C-5. And we flew the telescope all the way down to Houston, Texas, where there's a gigantic vacuum tank. It was big enough for the Apollo astronauts to practice walking down the ladder onto the surface of the moon so many years ago. Then when it was done testing there and we proved that it should work in outer space, then we put it back in the aircraft, sent it off to California, and finished putting it all together with the spacecraft bus and all the other warm parts, made sure it would fold and unfold properly. Then we closed it back up and put it in a shipping container. This is not the same one, but the ship that has taken it away from California has gone through the Panama Canal and is on its way to the launch site in French Guiana. French Guiana is a good place for a rocket because it's on the equator or very near, and it has a good line of sight towards the east, so it's not, if the rocket goes in the right direction, it will not fall on anyone. So that's a good place. Then we will push the button on December 18th, according to plan, and it will go up directly into space. And its launch time is approximately noon in Europe, about 7 o'clock in the morning here in Washington, D.C. So it will go straight on its way all the way out to deep space. We're sending it to a place called Lagrange Point 2, which is 1.5 million kilometers farther from the sun than we are. So this place moves around the sun with us And so the telescope will stay out there all year long. So it's about 1.5 million kilometers away, much closer than the other planets, but still 4 times as far away as the moon. It's far enough away that we cannot repair the telescope if we go there. So in future, we might have that capability, but right now we do not. Here is our movie of how the telescope will unfold in space. It is first to unfold the solar panels so that the battery does not ever run down. Then the antenna. Then the structure that holds up the sunshade, the umbrella. Now we are separating the spacecraft from the telescope itself so it can get cold, and unrolling the protective covers over the sunshade. This is all done by remote control. Of course, there is no astronaut anywhere near, and it's extremely complicated. So it has been very, very important for us to test and test and test, make sure this will work. We also have, where it's possible, 2 of every kind of electronic part, just in case some random part failure occurs. So this first part that I'm showing you happens in the first 2 weeks, get everything unfolded. But it will take altogether 6 months for the telescope to be completely prepared for scientific observation. So if we launch on December 18th, then in late June of 2022, we should be able to show you some beautiful scientific results. So, of course, we have a strong presence on the internet. You can look us up with Google or other searches, and you have many ways to track what we're doing. JWST, Webb Telescope, Webb, they're all good. By the way, James Webb was the NASA administrator who went to Jack Kennedy with a plan for launching the Apollo astronauts to the moon. And 8 years after he went to the president with the plan, the astronauts actually walked on the moon. So to me, that's a completely astonishing accomplishment. And it's hard to imagine how it was done. It seems like almost a miracle. But it was just people like you and me, who had a mission. So what are we going to do next? Of course, the Webb telescope will be powerful, and there will be more space telescopes going up. Europe is launching the Euclid mission. The United States is launching the Nancy Grace Roman Space Telescope in 2026. And as time goes along, we are building even larger telescopes on the ground. So here are pictures of the 3 gigantic ones that are already being constructed. The biggest one is European, and it is being built in the mountains in Chile. So when you think about what to do next, obviously, build a bigger telescope. This is wonderfully powerful, and I think we will all be very proud to know what it discovers, what people discover using it. So people often want to know, well, how far can humans go into space? So I don't know. But just to extrapolate a little bit from what we are already doing, we have already sent robots everywhere through the solar system to visit all of the planets, many interesting asteroids and comets and moons. We have brought back samples from some of them. We are learning how to divert a dangerous asteroid and keep it from hitting the Earth. So that's all robots. Robots are much more capable of doing things in a vacuum than we are. They are getting attached to better and better computers. As you know, computers can beat humans at almost every game that involves a board. They're not yet able to beat us at golf and tennis, but who knows how long that will take. People are very fragile. If you want to go to Mars, we have to protect you very, very well. You, of course, have to breathe because you can't stand a vacuum. We also have to protect you from cosmic rays, which are protons mostly that come flying through space and go right through our bodies, but they cause damage. So if you want to get there quickly, we need hardware that we do not have, such as a fusion drive. I don't know how that will ever happen, but of course, many people are working on it. Still, if you are a fan of science fiction stories, then we know that they can't actually be right. We have no current way of imagining, seriously, how to get a human being to a nearby star. The quickest we can go is thousands to hundreds of thousands of years. So even if you're a robot, you have to be extremely patient. But nevertheless, smart robots might be interested. Let's see what they do. So let me wrap up here and be happy to have questions. Thank you all.
Thank you for that fantastic presentation. Please, let's take a couple of questions. Come down here. In the meantime, we received several questions online. And so I'll just ask one online, and then we will take a couple of questions. Come here from the participants here. So the question I got online among 10, the one I like the best is, do you think that there might be life in other planets? And if so, do you think we would be able to recognize it? Do you think we can actually recognize if there is some other form of life in the universe?
I think the answer is yes. I think personally that life occurred very quickly here on Earth after there was the possibility. So as soon as there were oceans, we have fossils that say it did not take very long after the oceans were formed before we had fossil life. So that suggests from our one observation that life can happen easily and quickly if its conditions are correct. So I think that means we have a good chance to see life elsewhere in the solar system, because there are places which were wet, and some of them still are wet. So that's a good chance. For planets around other stars, we have a much harder problem because we can't go there to get a piece. We can, however, see what has life done, if it has, to the atmosphere. So here on Earth, we say life is responsible for creating oxygen. So if you were to look at another star, planet around another star, and see oxygen in that planet's atmosphere, you would be very tempted to say, we think it's alive. Now, I guess if other people would like to ask, well, how about intelligent life? And I think, well, probably, why not? But here on Earth, it's taken the entire history of the universe for us to appear. So that tells us that it's a slow process and maybe hasn't happened yet in many places.
Beautiful answer. We have many questions here on site as well. One of them is from my friend who is a PhD from Stockholm University in computer science and neuroscience, and he's a researcher at the Future of Humanity Institute at Oxford University. So he has a question, loud and clear.
Thank you. Beautiful talk, and as an amateur astrophysicist, I totally am in love with this telescope. But as a risk researcher, I'm a bit worried. This is a lot of things that can go wrong. We have put a lot of eggs in one beautiful basket. How do we make sure that in the future we get more baskets for our telescopes?
Oh, that's actually a wonderful question, because, of course, we knew that we had to build a telescope like this to make the scientific advance that astronomers asked for, and we knew that it was going to be very risky. So how do you make sure that something's very big and risky will still work? So 3 things. One is have 2 of everything where it's possible. So 2 sets of electronics, 2 ways to command everything to happen. One is to practice and rehearse, make sure that you do it over and over again until you get it right. And number 3, get some friends who are experienced. I like to say they're grouchy, people who do not like to be wrong, who will tell you when you've made a mistake. So we need all 3 things to have a chance to get this to work. And then you just have to do the plan.
Thank you very much, and the best of luck.
We have many other questions. Here we have a student from the Netherlands who is 20 years old, and he wants to ask you also about the future and about the space.
Hi, thank you for the nice lecture. So this concept, if I remember correctly, is 26 years old.
I'm sorry, you're muted. I can't hear.
Okay. So I'm muted. All right. Thank you, first of all, for the fine lecture. So if I remember correctly, the concept for this is 26 years old. Is the satellite you're sending into space not already outdated at this point? Or at what point did you have to decide this is what we're sending, and whatever we find after this or any technical advancements we have to skip?
So good question. This is the most advanced technology that we have. The only reason we can do this is we had to invent 10 new things. So for other telescopes, we have to invent different things. So this is actually the most advanced thing we could be flying today.
Okay, so at this point, you would not say that there's any technology that you're missing out on sending to space.
That's right. This is not obsolete, not at all.
Okay, thank you.
Yeah, thanks.
We have also several students, and here we have another one, 23 years old, from the Netherlands, please. Louder.
Yes. All right. Thank you very much for the talk. It was very insightful. I was wondering, since all the planets are moving away from us at an increasingly faster rate, do we run the risk of at some point, we do notice there's life at a different planet, but it's so far away from us and it's moving so quickly away from us that there's no way that we could ever reach it?
So actually two questions there. One is about things moving away. So the solar system is not expanding. We've measured very carefully. It's held together by gravity. It is the distant galaxies, the 100 billion stars held together by common gravity. Those are flying away from us. And it is true that in the very distant future, we think they will be flying away from us so far fast that we will not be able to see them anymore. But that's a very distant future.
Right. Thank you.
Many billions of years in the future.
So, Dr. Matter, we are very pleased. We have had many people following you live here in Madrid and streaming, over 2,000 people. So we are truly, truly happy to learn from you. And we are excited about the James Webb Space Telescope in December. We will be watching you.
Thank you. Wish us luck.
My friend, live long and prosper.
Thank you. You too.
Good.
And all of you.
Thank you. Thank you. Adios. Adios.
Adios.